North of southwestern Uvente Chasma, the plains open wide. Craters dimple the top half. Sinuous ridges snake between impacts. These ridges may be inverted stream channels. Former lows now stand as highs. Their beds resisted erosion. Cementing minerals could harden them. Larger rocks could armor them. Lava could fill the channel floor. Wind then strips softer grains. Water can carry fines away. In the lower terrain, erosion peels back layers. Light and dark bands form rings. The rings span about 1 kilometer. The smallest ring is the deepest layer exposed. Layers are common in Martian canyons. Yet the process that built them is unknown. The plain layers likely match canyon wall material. The scene reads like stacked time. Across the ground, a narrow line cuts the crust. Its trend is non-parallel to nearby troughs. That mismatch hints at a dike. Magma may have forced upward here. It could have fractured rock from below. Dikes are proposed to help form valles marineris troughs. They are also linked to surrounding grabens and pit chains. Seeing a dike at a different orientation matters. It can constrain how stress spread through the region. It can connect magmatic intrusion with tectonic stretching. Such geometry helps rebuild the sequence of events. The observation may refine how Valles Marineris evolved. It may be an important clue. It helps us better understand the magmatic and tectonic processes that occurred in Valles Marineris. A target site carries high-resolution infrared spectral coverage. CRISM flags interesting mineralogy here. The spectra are sharp, but the setting needs detail. HiRISE aims to fill that gap. High-resolution imaging helps interpret geologic context. It can show contacts, textures, and small landforms. That added context supports better readings of the mineral signals. It ties mineral detections to specific units. It also tests whether deposits are layered, fractured, or mantled. The goal is simple. Pair spectral clues with fine-scale geology. Then the story becomes constrained, not assumed. Without this coverage, the geologic setting is harder to read. With it, mineralogy and landscape can be interpreted together. On the trough floor, the mantle drops away. Ancient fractured bedrock lies exposed. Textures shift across the surface. A knobby unit rises in low relief. Raised circular ridges stand out. Sinuous ridge forms curl across the plain. Linear fractures slice through the rock. Possible wind-driven bed forms gather in pockets. Olivine was detected at this location. The scene supports a hard substrate. Wind has eroded it for a long time. Only a few wind-blown deposits remain. The ground reads as old crust, cracked, stripped, and lightly dusted. The lack of cover makes features crisp. It helps distinguish bedrock surfaces from later wind deposits. The site links mineral detection to a visible geologic unit. Along a crater wall, layers stack like pages. The wall exposes them cleanly. The objective is to study these layers in finer detail. Individual bands vary in tone and thickness. At least one layer appears light-toned. That contrast marks a distinct material within the stack. Tracking where it continues matters. It can define a single horizon across the wall. It can also separate one episode of deposition from another. Sharper views allow better mapping of contacts. They also reveal small breaks and ledges. Each step in the wall is a record of earlier conditions, now cut open by impact and erosion. The light-toned band draws the eye. It may be the easiest marker layer to follow through the exposure. A lovely crater sits with an eroded rim. The rim is worn down. Bedrock inside remains highly visible. Rock textures show through the surface. Slopes drop toward the center. On these slopes, faint streaks can appear. The goal is to study possible recurring streaks. Recurrence makes them worth tracking. The exposed bedrock helps because changes stand out. Rim erosion also reveals more of the substrate. By focusing on the crater walls, the study can compare different slope aspects. It can separate stable rock from areas where streaks form. The crater becomes a clean test site for surface activity. Some possible streaks run downslope, then fade with time. Repeated monitoring can reveal when they form and where they return. Steep scarps face toward the poles. One lies in each hemisphere. Their cliffs expose thick sections of ice. The exposed walls can reach 100 meters or more. The ice is described as nearly pure water ice. That purity makes it stand out against surrounding debris. Such exposures are rare windows into the subsurface. They also carry practical weight. Water is a key resource for future settlers on Mars. Accessible ice could support drinking water and other needs. These scarps therefore matter for science and planning. They preserve a frozen record of climate, and they reveal a usable reservoir close to the surface. The steep faces keep the ice visible. They mark a place where buried water is already uncovered. A triple impact structure spreads across the terrain. The full system measures about 21 by 14 kilometers. Here, the eastern portion drops toward a larger central crater. From that higher ground, deposits appear to flow downslope. They are interpreted as possible impact melt-bearing materials. The flow paths lead into the central basin. Where the topography levels out, the melt material seems to pond. It forms dark, smooth deposits on the crater floor. Outside the rim, ejecta looks different. In the northeast sector, it appears much rougher. The contrast separates pooled melt from thrown debris, revealing how the impact redistributed rock across multiple basins. The eastern sector shows the clearest transitions. Inside Turby Crater, sedimentary rock layers dominate the scene. Layer upon layer rises in stacked bands. These sedimentary layers record a history. They track Mars erosion and deposition over time. Water and wind are named as the key agents. Water can deposit sediment, wind can rework and remove it. The layered rock preserves what those forces left behind. It also preserves what they stripped away. Reading the layers is like reading past environments. The record is physical, not abstract. Beyond science, the terrain has a cultural pull. The layers make great landscapes for future interplanetary parks. They offer a place where geology becomes scenery, and scenery teaches geology. They invite exploration. North of Valles Marineris, a new crater breaks the plain. Incoming impactors excavate rock and spread an ejecta blanket outside the rim. From above, the blanket resembles a splash pattern. Dark tones mark part of this deposit. Small pieces are flung far out. Blue likely represents dark basaltic rocks. Basalt is a volcanic rock, common in places like Hawaii. Here it sits atop the dust-covered surface. Radial streaks extend from the crater. These rays are made of ejecta. Rays help identify recent craters in images. Older craters lack rays because erosion removes them. Impacts also expose the subsurface. This single crater becomes a window into deeper material. That is why impact craters are studied. HiRISE revisits this patch of Mars. It watches for change. Dust devil tracks are one target. Atmospheric vortices pass often, but they may not scar the dust. Most leave nothing visible from orbit. To tease out faint marks, the cutout is hard stretched. Brightest and darkest tones clip. That helps reveal subtle tracklets. Subtle contrasts rise from the noise. In the eastern part, several streaks run southeast to southwest. They could be dust devil tracks. Yet they also appear in an earlier HiRISE image. That prior view was taken about 1 month earlier. So these streaks did not form in the past month. The technique is built for detection. It makes delicate traces stand out. Nothing new appears this cycle. This western region may host a future set down. It is flagged as a potential mission location. The view is an enhanced color cutout. It highlights an interesting portion of the scene. Fractured bedrock is exposed across the surface. The rock is broken and patterned by fractures. Wind-blown dunes sit close by. Their sand forms distinct patches against the bedrock. The cutout emphasizes this contrast. Fractures become easier to follow. Dune patches become easier to separate. One unit reads as rigid ground. One unit reads as wind-moved material. This mix supports practical scouting. It can help judge what is stable. It can help flag what may shift. That is why this western region is highlighted for future planning and closer study. Beautiful, sleek Barchan dunes dominate the view. The scene is defined by that single subject. We have imaged these dunes. That is the stated focus. The dunes are Barchan. They are sleek. They are called beautiful. The terrain is presented through those dunes alone. Nothing else is foregrounded. No other feature is named. The dunes carry the entire observation. This is a deliberate look at one landform type. It is a record of how these dunes appear in this scene. The work here is capture. The dunes are the headline. The dunes are the study target. The description stays simple by design. It points and it stops. Beautiful dunes, sleek dunes, Barchan dunes, imaged, documented, and kept as the subject of this view. An impact crater cuts into the North Polar ice cap. The bowl is clear against the surrounding cap. On the crater floor sits an icy deposit. It occupies the interior as a distinct feature. The scene pairs two ice signals at once. The cap forms the broader setting. The floor deposit adds a second layer. This is an impact crater on the North Polar ice cap. The deposit on the floor is ice. That is the key fact. The crater is the setting. The floor deposit is the content. The deposit is contained within the basin. The cap surrounds the impact scar. The floor holds the icy material. Both are shown together. The observation centers on that interior. It keeps attention on the floor, where the icy deposit rests. A depression holds a group of gullies. The observation targets that cluster. The objective is examination. Pictures like this help map gully distribution. Mapping needs clear examples. This site provides one. Gullies are present here, but they are not common in this region. The note is explicit. Compared to many other places, there are not many gullies. That scarcity makes each group valuable. The scene becomes a reference point for where gullies do exist. It supports broader surveys across the region. By recording this depression and its gullies, the dataset gains another mapped location. This is why the cluster is singled out. The focus stays on the group and on how uncommon gullies are here. Thank you for being with us. Please subscribe, share, and like.